Entropy Part 2, looking at entropy and spontaneity. The second law of thermodynamics relates to increasing entropy in the universe. A spontaneous process must have increasing entropy in the universe overall. For the second law of thermodynamics, a process can only be spontaneous, as written, if the entropy of the universe at standard state increases. This is the cause of the quote-unquote heat tax that we mentioned earlier, that the universe extracts. We must deal both with inefficiency as well as a loss of energy to increase the disorder of the universe. This occurs because a spontaneous process has to input energy into a lower temperature heat sink in order for it to occur. So you have to go from higher energy to lower energy for a spontaneous process to occur. All energy flows downhill. A positive entropy change of the system will favor spontaneity. But the entropy change of the system does not have to be positive for a process to be spontaneous. All that has to occur is the overall spontaneity of the universe has to increase, or the overall entropy of the universe has to increase. The entropy of the universe is equal to the entropy of the system plus the entropy of its surroundings. As long as the combination of the two is positive, the entropy of the universe will be greater than zero in its change, and the process can be spontaneous. If temperature and volume are constant, the system does not interact with its surroundings, so in this case, surroundings goes to zero. Thus, in that instance, the change in entropy of the universe is equal to the change in entropy of the system. A positive change in entropy of the system favors spontaneity. A negative change in entropy of the system disfavors spontaneity. Looking at the change in the entropy of the surroundings, the change in entropy of the system can be negative in a spontaneous process and positive in a non-spontaneous process. If I freeze water, freezing water causes the water to become more ordered rather. As it becomes more ordered, its entropy decreases, so the change in entropy is negative. Melting ice causes the ice to become less ordered, more disordered. So this is a case in which the entropy of the system will become positive. It will increase as it starts to move from a solid to a liquid and become more disordered. The process of freezing releases energy to the surroundings. So the change in energy of change in entropy of the surroundings is going to be positive because it's absorbing energy from the system. In the process of freezing, this change in energy to the surroundings is greater than the change of entropy to the system, which is negative. So the positive change in the surroundings is greater than the negative change of the system, which means the overall net difference is positive for the universe. In melting, it absorbs energy from the surroundings. But even though the surroundings are negative, giving off energy, the amount of energy it gains from the increasing entropy of becoming more disordered is greater than the energy that is taken from the surroundings. So once again, the overall combination of the negative surroundings and the positive system is positive, giving us a positive change in energy. In both of these cases, change in the entropy of the universe is positive. The energy gained or lost by a system affects the entropy of the surroundings. A loss of energy increases the entropy of the surroundings. Absorption of energy decreases the entropy of the surroundings in proportion to the amount of energy gained or lost. So the change in entropy of the surroundings is proportional to the opposite of the change in heat of the system. The change in entropy of the surroundings is also proportional to the reciprocal of the temperature change. If temperature goes down, the surrounding goes in the opposite direction. So its surroundings will go up as temperature goes down in the system. Surroundings go down as temperature goes up in the system. So overall, the change in entropy of the surroundings is proportional to the negative heat of the system over its temperature. Or the change in entropy of the surroundings is equal to the negative enthalpy of the system divided by its temperature. We cannot measure the entropy of the universe directly. All we can do is report in terms of the system. Because of this, usually the subscript cis is omitted, leaving us with delta S naught or just delta S in what we deal with entropy. Now, entropy is temperature dependent. Enthalpy is measured in joules or kilojoules, but entropy is measured in joules per Kelvin. Freezing water is a spontaneous process, but only below 0 degrees Celsius. If I leave water out at room temperature, it does not spontaneously freeze. This is because the magnitude of the change in entropy of the surroundings is also temperature dependent, as we just saw. The entropy overall measures energy per unit temperature. The higher the temperature, the effects of additional energy are less. Consider that temperature is a measure of average thermal energy. Higher temperature means that additional energy is being added to what is already a high amount of energy. This will cause less overall difference to the state of the thing that we're adding the energy to than if there was less energy. As an analogy, if I were to give you $1,000, that will most likely change your net wealth a lot more than giving $1,000 to Bill Gates would, overall, as a percentage of your net wealth. In the same way, adding 1,000 joules to a system with high energy, and thus high entropy already, disrupts the system less than adding the same amount of energy to a system with low energy, and therefore lower entropy. This explains why the changed entropy of the surroundings is temperature dependent, where it is equal to the negative enthalpy of the system change divided by the temperature.